In this video, we will discuss the factors or the conditions that affect the rate of a reaction. And this is what kinetics means. Kinetics in chemistry means how fast does a reaction occur. And so the way we typically will measure how fast a reaction will occur will be concentration per time, per unit time, and concentration can be measured in molarity, and so that would be moles per liter, so we could say molarity, and then the generic unit for time will be seconds. Okay, and the rate at which something is consumed is going to be called the rate of disappearance, and that is sometimes given a negative sign to indicate that your reactant is disappearing, whereas something called a rate of appearance is generally positive, and it's generally referred to for your products which are being produced. There's a lot of different ways that you can measure a reaction rate, and we will do a couple of these in a couple labs that we'll have. One of them is we can just watch, probably from your experience in chemistry, you've been able to watch a reaction and you've been able to see when the reaction is done. And so another would be actually measuring the change in pressures, and we would use a pressure gauge for that. We could monitor the pH. We'll do that plenty of times in acids and bases, and we would use a pH probe, or sometimes that's called a pH meter to do that. We could monitor how things change in light, and that's what we'll specifically do in this unit, and we would use a spectrophotometer or a spectrophotometry for that. We can monitor the mass, and we could analyze the sample after a set amount of time, and so maybe every 10 seconds or so, and that's what we'll do actually in lab. We'll have a timer, and every 10 seconds maybe we might measure the absorbance from our spectrophotometer. And so what we could produce if we wanted to, and we'll actually produce some of these, is graphs showing how the concentration or how the molarity changes over time. And in this graph, I put minutes, but oftentimes it'll be seconds. And a graph like this is something that we can get a lot of information from. Specifically, I know that NO2 must be a product. How do I know that? It has a positive slope. Okay, meaning it is being produced. And I could say the same thing for O2 as well. So I could change this to NO2 and O2 because they both have positive slopes, whereas N2O5 must be a reactant. The way I know that is that that blue line is going down, meaning it has a negative slope. So what I can do is I can write a reaction that N2O5 must be breaking apart or decomposing into NO2 plus O2, and I could make a T-chart and I could balance this, or I could be a little bit clever and I could look at my graph and say, okay, my N2O5 decreased by what looks to be 2, where my O2 increased by what looks to be 1, and my NO2 increased by what looks to be 4. And so if I do that, that actually ends up balancing, and that is not by coincidence. That is actually on purpose, because this ratio that we have just made in this balanced chemical reaction is what's represented graphically here. So let's go through and discuss a lot of different factors that influence reaction rates. The thing that we need to understand completely, though, is that Particles must come in contact in favorable orientations, and they must have enough energy to actually cause or activate the reaction. And the rate of a reaction is going to depend on how frequently these collisions are and how efficient they are. So if I think about a state of matter, the surface area of something like a solid and liquid is a lot, and so liquids and solids are a little bit easier to get to react, whereas gases have a lot of space, a lot of empty space between the particles. And so because our particles have to come into contact with each other, gases actually are kind of difficult to get to react because they're so far away from each other. And that's why liquids and solids are a little bit easier to react. And it might not be surprising, but the more molecules we have present, the more collisions that are likely to occur. That doesn't mean they'll necessarily be successful collisions, but we increase our likelihood that we would get a successful collision. And it's not just a 2 or 3 times more likelihood. It's really an exponential relationship, because there's a lot more combinations that could happen if we have more reactants, such as in D. There's a lot of different combinations, and if this were a math class, we could calculate that. If we increase the temperature, we're going to increase the speed of our molecules, and that's going to be a direct relationship. And that's going to give our molecules more energy, and so it's more likely that they will overcome the activation energy. And a general rule, this just is not based on any sort of law, but this is more based on observation, that if we increase our temperature by 10 degrees Celsius, or we could even call that 10 Kelvin, that will oftentimes double or get close to double the reaction rate. And that's something that AP Chemistry has been known to ask before. But here is what's really, really important. And I'm going to highlight it in pink because it's just that important. The only thing that temperature changes is the rate constant. And we have not talked about that yet, but that will be little k. Okay, so that is important. We'll talk about that later. Catalysts are important because catalysts allow a way for a reaction to occur faster. And a couple things about catalysts that we want to make sure we know is that catalysts, they increase the rate of our reaction. However, catalysts are not consumed in a reaction, but catalysts do react. So if I start with 35 grams of platinum, I'm going to end up with 35 grams of platinum after my reaction is over. Here's what you want to know, and I'm going to highlight that one in pink as well, that catalysts lower the activation energy. And AP doesn't typically ask this, but homogeneous catalyst means that it's in the same state of matter as your reactants, whereas if it's a heterogeneous catalyst, it's in a different phase of matter. Okay, it's important that our reactants need to collide, of course, for the reaction to occur, but they have to collide in the correct orientation. So what I have drawn here is that we are producing F2. And so the easiest way for that to happen in this reaction is that if our fluorines come in contact with each other. So if I take this molecule and try to slam it into the other molecule in this orientation, I'm not going to get a reaction. My fluorines aren't close to each other, and so that makes sense that that's going to give us no reaction. However, if I get my fluorines really, really close together and I try to slam those molecules together, it's definitely more likely that I'm going to get my F2 product. Okay, and collisions have to occur with a certain minimum energy, and that's called the activation energy. And activation energy is commonly abbreviated capital E with a subscript A. Okay. activation energy, if I look at it from a graph perspective, let's say I have a generic reaction, A plus B goes to form C. I could say my reactants are A and B, and they form C, so that's my products. But my activation energy is this little hump that I have to get over. Okay, and what happens at the top of your hump, or the very highest energy on my graph here, is called the activated complex, and that is sometimes called the transition state. And in a transition state, that is when bonds are being broken and being formed at the same time. And so that is why that is so high in energy, that there's a lot going on, and it's a very unstable situation, because I'm breaking bonds while simultaneously forming bonds, and so just a lot of energy. Here is how catalysts affect your activation energy, and I've drawn here, this is the black curve is just your normal reaction. And this red curve is with a catalyst. So what I like to think about how a catalyst kind of works is it's sort of how I teach labs in a lot of ways. So this black curve might represent how I would normally explain how to do a lab, with each step very detailed, and it might take a little bit longer if I explain it that way, but there's no confusion. Whereas this red graph, and maybe I should use a highlighter here, this red graph represents a more efficient way to do something. So if I was going to do a lab all by myself, not worried about teaching it, I'm definitely going to be able to get it done with a lot less energy and a lot less time. And so that's kind of how a catalyst works. It might go through some different steps and it might look a lot different, but it still ends up at the same reaction. And so we have a lower activation energy than we did before. The last thing we'll talk about in this video is graphs that look like these, and these are distribution graphs, and we want to make sure we understand how to read these, because it's very common that chemistry students kind of get a little bit confused on these. And this uses integrals, which is a calculus thing that we're not worried about here. But what we want to look at is we've got this curve, and I'm going to highlight it here. And they generally are in that shape. And the area underneath this curve, so what I'm highlighting, represents our particles. And so what we have here shaded in blue, those are the particles that do not have enough energy to react. And the reason why is that they are to the left of our activation energy. Whereas the particles with these blue lines, those represent our particles that can react because they do have enough energy. And so if I increase the temperature, what that means is I'm going to have more energy, and so more particles are going to be able to react. So I'm going to make sure I make a point at my activation energy, and I'm going to draw with a dashed line what my graph might look like. So I'm definitely going to have more particles, or more area here, that particles, more particles that can react. However, to the left of my activation energy, because I have more particles that can react, I'm going to end up with less particles that cannot react. And so my graph might actually have fewer particles or fewer shadings here because I've increased the temperature. So less particles will stay stagnant, if you want to think about it in that way.